Thank you, Engine. And in the past, we thought of encrypting only sites or between sites, and today we even have to consider between our keyboard and the device that we want to communicate with. And with this thought, I would like to present our next speaker, Dr. Eran Tromer. He's a faculty member at Tel Aviv University, where he heads the Laboratory for Experimental Information Security. Dr. Tromer received his PhD at Weizmann Institute of Science and previously pursued his research at MIT and at Microsoft Research. His research focused on low-level platform risks such as side channel attacks and on cryptographic mechanisms for conducting trustworthy computation on faulty platforms. Eran Tromer, please.
Thank you. It's an honor to be here, and I'm privileged to have this opportunity to tell you about research done in my lab with my student Asa Naveh on the challenge of authenticating images. Let's start with some motivation. Digital photographs are nowadays everywhere, and they're often used as evidence that a certain physical scene once existed. And this happens in legal context as legal evidence, it happens in journalism, it happens in politics, in various social contexts, in particular shaming or extortion as bad examples, but also positive examples like a dating website. And even the most important use of photography on the internet, the use that often stretches our credulity about physics and physics, namely cat pictures. In all of these contexts, when we see a picture, we tend to believe it, but is it really trustworthy? And of course, we know that with the very easy availability of image processing tools, whether expert or highly automated, we can't really trust what we see. Just to take one example, for the dating website, well, faking images, there's an app for that. There's an app called Facetune that fixes minor blemishes, proportions, and whatever you instruct it to. So, in this reality, can we really trust images? And there are good reasons to trust them, good reasons not to. And looking at the history of photographic evidence, there are many famous examples of fake images, some of which made it to the leading news agencies, some of which are now the subject of a DARPA research program. This is clearly a major issue. So what we want is a method for authenticating images, a scheme that allows a camera to capture an image and then send that image to a viewer. And we'd like to play a game of a prover and verifier so that the viewer can somehow check a proof generated by the camera that originated the picture. And there's an easy way to do it, a trivial way, which is using plain digital signatures. And indeed, this has already been deployed in some cameras, for example, the high-end cameras by Canon and Nikon. And they have embedded digital signatures, and they signed every image. Unfortunately, the particular implementation is preposterously bad and extremely insecure and was completely broken, but not for any good reason. It could have been done much better. But there is a basic problem with this approach, because if all we have at our disposal is basic cryptographic signature schemes, well, what they attest is that an image was not modified since it was signed. But in most uses, we actually do want to edit images after they are captured for functional reasons. For example, we get out of camera a 24 megapixel image, 6 megabytes in size. And then we want to post it on Facebook into this tiny window where it needs to be a tenth or a hundredth of the size. Sometimes we want to adjust brightness, contrast, cropping, rotations, and so on, all of which are legitimate transformations in most contexts. They preserve the authenticity of the image in terms of representing the reality that was captured. But not all transformations are legitimate. For example, if you're on a dating website, changing the width to height ratio may not be within the legitimate rules of the game. So what do we want from such a scheme to fulfill all of our goals? Well, we wanted to support any specified set of permissible transformations. For a particular application, we want to decide what's legit and what isn't, and have a scheme that allows us to restrict transformations to that particular set. We also want to be able to support a sequence of editing operations. Maybe first privacy adjustment, then the image is downsized and then rotated. This is still fine. And maybe different users do these subsequent processing steps. Of course, we want soundness. We want the proof to be convincing. So the verifier algorithm that inspects the proof will only accept it if indeed it is the result of a legitimate sequence of transformations. And we want, for efficiency, we want the proof to be short and easy to verify. Imagine a proof being attached to an image in Facebook. It will be viewed by perhaps millions of people. It will be verified by perhaps millions of people. We want this to happen very efficiently. And lastly, and this is perhaps less obvious, but actually very important, we want a zero-knowledge property. Proofs should not reveal anything beside the fact that the image is authentic. And let's look at a particular use case. Again, dating websites. Photos should reflect what the potential dates really look like. And it's fine to go through some sequence of transformations, such as the ones I mentioned earlier. Cropping, for example, is perfectly legitimate because people may want to hide their surroundings and focus on their beautiful face, and they may have very good reasons to hide their surroundings. And we want to preserve their privacy and not leak any of that context when it's deemed irrelevant. So this problem is very natural, and in fact it has been studied over dozens of papers for decades. And up on top you can see the basic digital signature scheme. It's very nice, it's small, it has small error, but it does not support any transformation. And then there's a sequence of works, most of which are based on robust hash, that take basically a signal processing approach. They do some image processing transformation on the image. For example, taking a Fourier transform or a Don transform, or looking at pairs of JPEG coefficients, all sort of things like that. And then they get a summary of the image and sign the summary. And the point is, if that transformation that they apply, the transform that they apply, say they are Don transform, is invariant under, in this case, rotations, then the signature will be preserved even if the image is rotated. Very cool trick, but it's specific to specific transforms and specific editing operations. And you can see that none of these prior schemes actually supported everything because of this very restricted approach. They also had very high error rates. The most pertinent scheme that is closest to what I'll describe is the PhD thesis of Walsh from a few years ago, who used trusted hardware to get attestations at the hardware level that the computer doing the operation was running the right software. But that did require extra hardware on every editing station. And what I'll tell you today is about PhotoProof, a system that we developed that does not use any hardware, that it allows any transformations to be done, and it preserves small proofs regardless of the type and number of transformations. So here's how PhotoProof works from a functional perspective. First, there's a setup stage where the system administrator, say the dating website webmaster or the newspaper editor, decides what transformation they allow. They provide a specification in the form of a list or a form of code that gives formally the list of permissible transformations, and then they release some public keys for everybody to use that encode that choice. And then, for the rest of the system's life, over and over, pictures are taken, and then they are edited. When the image is first captured, it's accompanied by a plain signature. But after editing, the edited version is accompanied by a proof. And the proof can convince everyone along the stage until it reaches the final viewer, who can really be convinced that the image resulted from such a sequence. However, if someone tried to apply a different editing operation, say airbrushing the image, then there's no way they can create a convincing proof. Whatever they claim will be rejected by the viewer. Now, the approach we take for this, to implement this functionality, is a very general approach called proof-carrying data, joint work with my student Alessandro Chiesa. Proof-carrying data is a very general methodology for taking distributed computation and ensuring invariance in this computation using cryptographic tools. So we have some network of nodes. In our case, these are image editing nodes, and we don't trust any of them. And then we want to attach proofs to every step to create that trust, not by trusted hardware, not by checking their passwords or checking their security clearance, but by making sure that the computation that they perform fulfills our specification. And our specification is given by a compliance predicate, something to be checked at every individual node. And the proof that is attached to every node attested that this node complied with that predicate, and moreover that all of its inputs likewise complied with that predicate. The specification of that predicate says what's coming in our case the old image, what comes out, in our case the new image, and some local input, in our case the choice of transformation and its parameters, like by what angle to rotate the image. So we can use PCD for the case of authenticating images by treating the life cycle or provenance of an image as a distributed computation and encoding a proof-carrying data compliance predicate for the permissible transformations. And then after we encoded a compliance predicate, say for cropping, rotations, and flips, we can fulfill the functional goal that I described earlier of attaching suitable proofs and maintaining soundness and even zero knowledge. So this is, I think, a very interesting mapping, taking an open problem coming from the image community and applying state-of-the-art cryptographic tools. And we set out to understand whether this is really feasible. To do this, we used our implementation of proof-carrying data coming from our open source library, the libsnark library, which provides a general implementation of proof-carrying data. I will not be able, under the few remaining minutes, to describe the cryptographic mechanisms underlying libsnark. But from a bird's eye view, you can imagine that what it does is create a template for what a correct node looks like, what a correct execution of the compliant predicate looks like. And then the proofs show that the actual operations at the node match the template. And the cryptographic machinery underneath this idea is rather non-trivial and is covered by this sequence of papers and some more recent ones. Our prototype supports color images, and it supports a variety of transformations, cropping, rotations, transpose, brightness, contrast, and so on. And there are many challenges in implementing this. The conceptual mapping is very nice, but there are many theoretical challenges that come out in how to properly define things so they actually make sense. And there are also strong non-trivial engineering challenges in terms of performance. We have generic tools that would allow us to do this very easily but very inefficiently, and we spent a lot of time finding ways to encode image transformations as arithmetic circuits over large finite fields of just the right form in order to get several orders of magnitude improvement. And the bottom line is this benchmark. Let's take, for concreteness, it is fairly small images, 128 by 128 pixels. Not very large, but it's obviously the right size of image because an image is worth 1,000 words, and 128 by 128 pixels is roughly the same entropy as 1,000 words. I did the math. And what you can see is that there's a proving key I mentioned. It's a bit big, almost 3 gigabytes, but hey, it's smaller than the Bitcoin blockchain, so who cares? Proving time is a few minutes, which is awkward, but hey, it's just the first prototype. The good news is that the proof is just a few kilobytes, and verification time is less than a second. So already in this first prototype, after the editing is somewhat more expensive, but verification is very, very practical. Now this can be embedded as a plugin in GIMP or Photoshop or your browser. And we have many extensions that we discuss in the full paper, like authenticating metadata, the geolocation tags, editing history, adding certificates and public key infrastructure. I won't go into any of these, but there is a lot more functionality that we can piggyback on and add to the scheme once we realize that there's this mapping and we can have more logic in that compliance predicate. You can find the paper in the recent IEEE Security and Privacy Conference, or this URL. This paper, up to the performance caveat, solves an open problem that's been open for a few decades and dozens of papers. It also creates opportunities for interesting research and open problems. First, improving performance. Second, going for the next stage of the attack, which is attacks at the physical sensor level or just faking a physical scheme. We discussed that in the full paper as well. And I think most excitingly, we can do analogous things. We can apply the same proof-carrying data idea to other domains in digital media, like provenance of text or provenance of audio recordings, or provenance of databases, assuring the integrity of confidential or sensitive parts inside a database. If there are people in this audience who need some of these tools or have ideas for applications and additional uses, I'll be very happy to discuss this. And in the meanwhile, thank you, and I'll be happy to take questions. That's a great question, and one of the extensions we discuss, we can embed these proofs steganographically into the image so that it is robust even to things like recapturing. We are looking for the right application domain to test this. Right, this is an interesting question. Can we support transformations that preserve semantics of text but allow re-editing it? And the answer is that we do need a formal specification with the compliance predicate. So if you have a set of heuristics, then we can encode these. So encoding the compliance predicate, expressing what you want to be enforced in a natural language is an open area of research. It started out as a very low-level representation using arithmetic circuits, and in an upcoming paper we show how to do this instead using high-level languages like Java.